Hey guys, this is my magnetic field of a bar magnet lab or lab 2. So the purpose was to investigate the distance dependence of the magnetic field due to a small bar magnet by measuring the on and off axis magnetic field values experimentally and computationally. So an overview of how we did that was we first used an experimental model involving a magnetometer and a smartphone, tape, and measured the magnetic field due to a permanent magnet at various distances, being a bar magnet, and also developed a computational model using the Biot-Savart law to simulate and compare the measured magnetic field to computational values. So some of those principles, like what we just talked about, is that law describing relationship between the magnetic field at a point and current, the distance dependence for the magnitude of a bar magnetic field, which describes the magnitude of the magnetic field for a bar magnet and how it decreases with distance, and then just the bar magnet acting as magnetic dipole, so it describes the properties of a magnetic dipole as a closed circulatory electrical current system spinning about given axes. Some of our results were a magnetic dipole moment mu of 3.32 Newton meters per Tesla, an N value of negative 3.125, which is supposed to be negative, experimental magnetic field being 6.46 times 10 to the negative fifth Teslas, and then a computational magnetic field being 4.69 times 10 to the negative fifth Teslas. So some of those formulas breaking down fundamental principles included the Bussard law. So how this is essentially what we used in this form in the computational model to represent the function of the net magnetic field. We used the fall-off formula, kind of what I just talked about, that distance dependence formula, and used this linearization to represent the x component magnitude and then derive our k and n values in conjunction with this, the dipole component breakdowns of the magnetic field, and essentially using the on-axis version to find our magnetic dipole moment. So the key assumptions for this lab were that the bar magnet acts as the magnetic dipole, so looking at those on and off axis parts and fields, and then also that the magnetic field must fall off with increased distance. So that was essentially given to us here, and that's what we used basically to derive everything. And so going into our procedure, for the experimental part, we first had to download a magnetometer app that, measured the magnetic field due to a magnet and not GPS, compensated by orienting our phone orthogonal basically to the Earth to offset any of the effects that that may have to our results, and then used basically tape measures and pieces of tape to locate the magnetometer chip within my iPhone, which was in the top corner, like shown here, and measured the distance between the bar magnet and phone's magnetometer for specific X component magnetic field magnitudes for on and off axis measurements. So in our observations for the experimental model, we saw that the system was the bar magnet and surroundings were everything else. On and off axis measurements, so off axis at 45 degrees, off axis repeated measurements for different desired magnitudes were displayed here in a given Excel sheet. And so it allowed us to plug in our experimental values for the non-linearized version of the fall formula to derive our constant K and N. And so basically using everything that we had here, and it gave us this formula. So this was a representation of N, and this was ln K, which we'll show in just a second. And this also represents our experimental net magnetic field. So yeah, this is the breakdown of how we were able to get our basically N value right here, which was negative 3.125, our K, taking the e to the ln K for this to cancel out the natural log, and that gave us 6.68 times 10 to the negative seventh, and then calculating our magnetic dipole moment here. So that was basically we got as our initial conditions to plug into the computational model. And so in terms of our observations, the first and last one were proven to be true, as they were consistent with what we saw in the experiment for this lab with the fall-off formula in mind, while the other two were false. So this was some of our code plugging in that magnitude of the magnetic moment right here. I mean, the N value right here. This was that formula, as we said earlier, using Biot-Savart law. And then this is what we were able to derive in terms of our full computational model you will see in just a second, but basically just taking the magnitude of these components here to get our computational value. And then this was given in that Excel sheet, like I said, so you can see that that's larger, which is probably due to some of our assumptions. But yeah, this is basically when we were just making those arrows that you saw previously for the perpendicular arrows and everything, and then the 45-degree angle. So if we had oriented our setup differently, that magnetic field would have interfered with the bar magnet's magnetic field, drastically altering our results. And so that's why we had our procedure designed to measure simply the permanent dipole. And then if we had stuck two identical magnets together, the magnitude of the magnetic field would double because of the identical properties of the magnets, but the direction would have remained the same. And then some of the errors are that there were probably other magnetic objects generating magnetic fields. And then our measurements in terms of the Y components probably didn't stay the same the entire time. And yeah, thank you.